Hello, welcome back to Mammalian Anatomy at College. Here we're going to discuss Chapter 16, the Special Senses. And in this video, we're going to start our conversation about the ear. The ear is an amazing organ, and because it's not only responsible for hearing, it is also responsible for equilibrium. So allowing our body to balance itself. And so in future videos, we're going to look at the physiology of hearing, and we're also going to look at the physiology of equilibrium and learn how the ear is capable of allowing us to detect linear acceleration and rotational acceleration. But before we get into the physiology, we always have to start out with the anatomy because structure begets function. So let's hop into it. So the ear is divided into three regions: the external ear, the middle ear, and internal ear. And this is an image that is going to kind of show those different regions. Here we would have the external ear, the middle ear, and the internal ear. So the middle ear would be located here, and the inner ear would be located here. Much of our conversation will be on the inner ear because it is very complex, and it is what is specifically responsible for allowing sound waves to be converted into action potential. And there are specialized regions of the inner ear that are going to help us be able to look at static equilibrium, linear acceleration, and rotational acceleration. But let's take each step at its time. So first, let's talk about the external ear. The external ear is going to include the auricle, or what is also known as the pinnae, the external acoustic meatus, and the tympanic membrane, which is usually called the ear canal. The auricle is really important because it will actually funnel sound waves into the external acoustic meatus and then towards the tympanic membrane. And the structure of the auricle is very, very cool because it has the capability of allowing us to have stereoscopic hearing, meaning when we use both of our ears, and because our ears are slightly different positions from each other and the ears have a unique shape, they are capable of allowing us to hear objects and pinpoint where they are in three-dimensional space. And as I had just mentioned, the shape of a person's ear is really important for that stereoscopic hearing. Each person actually has a unique ear shape that is as unique as their fingerprints. And the ear and the brain have developed together so that the brain can understand how sound waves bounce off the person's unique ear shape, and then can use that information to determine where a sound is originating from within the environment around us. So that is pretty cool. I think that is amazing. And some researchers actually have been studied this, and they actually put clay in the ear or clay in the folds of the ear to change its shape. And researchers found that individuals whose ears have been modified with clay were not able to pinpoint where a sound came from in the three-dimensional space. So that is kind of cool. So your ears are as unique as your fingerprints. So that is amazing. The next region is going to be the middle ear, and the middle ear is going to be a bony hollow located here, and the bony hollow is going to be close to the petrous region of the temporal bone. And within this bony hollow, there are going to be 3 ossicles, 3 tiny bones. These bones are so tiny that they can all fit on a dime. And so that is kind of cool. They're the tiniest bones of the human body. And they are named based on their structure. So let's kind of talk about them. So this one is going to be the malleus. This one will be the incus, and this will be the stapes. Malleus gets its name because it's not only going to look like a hammer, but it also is going to act like a hammer when we're looking at the conduction of sound. This one is going to be the incus. Incus means anvil in Latin. So the malleus is going to hit the incus. The hammer is going to hit the anvil. And here we have the stapes. Stapes refers to stirrup. So if like a person is riding a horse and they are putting their feet in that little structure, that's stirrup, the stapes has that shape to it. So that's why it gets its name. So as sound is moving through the ear and being transmitted into mechanical energy, what will happen is the tympanic membrane will actually vibrate back and forth over here as sound hits it, and it will vibrate at the specific frequency of the sound. That vibration will cause the malleus to vibrate, and it will make the malleus hit the incus. And the incus will then move the stapes back and forth. And as it does this, it's going to kind of amplify that sound or amplify that vibration. And it's going to have it at the same frequency as the sound. And it's going to vibrate back and forth like so. Before I leave this slide, I do want to describe 2 more structures. There are 2 kind of membranous windows that are going to connect the middle ear and the inner ear. Over here, what we're going to have is we're going to have the oval window. The oval window will connect the stapes to the inner ear, and what will happen is the stapes will push on the oval window and create pressure waves within the fluid of the inner ear. Here we have the round window. The round window will actually alleviate those pressure waves that the stapes created. So I'm just making a note of this for now. We're going to We're going to talk more about that when we get into the physiology of hearing. There's a tube that is in the middle ear that will connect the middle ear to the throat, to the back of the throat, and we call that the pharyngotympanic tube. The back of the throat in anatomy is called the pharynx, and so that's where it gets its name. It connects the tympanic membrane to the pharynx. And the function of this tube is to actually equalize pressure on either side of the tympanic membrane. So why is that important? If the pressure isn't equalized on either side, the tympanic membrane will not be able to vibrate freely. And as a result, it won't be able to transmit or conduct the energy or the vibrations that the sound waves bring in. And so when are going to be situations when there is going to be an imbalance of pressure on either side? So for example, when you're flying, there will be lower pressure on the outside of the tympanic membrane rather than in the middle ear. So diving in deep water would be another situation where there'll be a difference in pressure. And how is this pressure equalized? Well, when we swallow, what will happen is it will actually cause the opening in the pharyngotympanic tube within the pharynx to open up, and it will allow the air to be this same pressure on either side. This is why, like chewing gum or swallowing can actually help help your ears pop when you are flying and those sorts of things. Oh, here we go to the oval window and round window. We already talked about these. These are membrane lined holes that will connect the middle and inner ear. Okay. Now what we're going to go into is the internal ear or the inner ear, and this is going to be a bit complex. So we're just going to take it step by step and kind of describe each of the regions. So a second name for the inner ear or the middle internal ear is going to be labyrinth. So labyrinth refers to a maze, and it gets its name because it is a complex kind of maze that is found within the skull. There are two divisions of this labyrinth: the bony labyrinth, which would be the hollow spaces that are going to travel through the temporal bone to allow for there to be space in the bone for the inner ear. So the bony labyrinth is bone itself. It's more of a hollow space, but many times what can happen during dissection is that the inner ear, the bone around the labyrinth can be carved away, leaving just the barest edge of the bony labyrinth so that you can see the internal structures itself. Within the bony labyrinth, there is going to be a membrane that is going to follow the shape of the bony labyrinth, and we call this the membranous labyrinth. And so both of these are going to be really important for the physiology of the ear. So, as I said, the bony labyrinth is hollow spaces that are found within the temporal bone, and it's going to be specifically within the petrous region of the temporal bone. And the bony labyrinth is going to kind of have three areas. It's going to have the semicircular canals. So there are going to be three loops over here. We'll see that these three loops play an important role in understanding rotational acceleration. There is going to be the vestibule. Vestibule in Latin is an entryway, and so this is going to be kind of the entry hallway of the inner ear. And there are going to be special structures in here that are going to be responsible for understanding linear acceleration. And then the last thing, last region of the bony labyrinth is going to be the cochlea. Cochlea means a snail shell, and you can see it does have that shape to it. The cochlea is going to be responsible for hearing. So we have the semicircular canals for rotational acceleration, the vestibule, which will be important for linear acceleration, and also static equilibrium. And lastly, the cochlea, which will be responsible for hearing. Within the bony labyrinth, we're going to have the membrane or membranous labyrinth, and the membranous labyrinth is going to just be essentially a bunch of tubes and sacs that are going to fill the bony labyrinth. It's mostly composed of simple squamous epithelium. However, there are going to be some regions that are specialized and will kind of thicken and be composed of different types of tissue to allow for sensation and for housing sensory receptors. Again, there's going to be membranous ducts that are going to be within the semicircular canals. Within the ventricles, within the vestibule, there's going to be the utricle and the saccule. These utricle and saccule will be able to understand that acceleration. And we're also going to have the cochlear duct, which will travel through the cochlea and aid in hearing. Here is it a little bit not wider, but larger. So in this kind of, well, it's a bony color. The bone, it's going to be the bony labyrinth over here. And in blue, you'll see the membranous labyrinth traveling through. In the internal ear, we're going to actually have fluids that are going to fill the bony labyrinth and the membranous labyrinth. The endolymph is going to fill the membranous labyrinth, so endo meaning within. And the perilymph, meaning around, is going to fill the bony labyrinth. It's going to fill the space between the bony labyrinth and the membranous labyrinth. And this fluid is going to be actually continuous with the cerebral spinal fluid and kind of be filtered through. It is important to note that the endolymph and the perilymph never unite. They are always going to be consistent and separate from each other. Okay. So if we're thinking about where these fluids exist, within the membranous labyrinth, we're going to have the endolymph, and between the space of the membranous labyrinth and the bony labyrinth, we're going to have the perilymph. This will become much more important when we're looking at the physiology of hearing. We'll see that pressure waves will actually travel through these fluids and impact the shape of the membrane and affect sensory receptors within the cochlea. So now let's talk about the cochlea. The cochlea is going to be a region of the internal or inner ear, and it's going to be a snail shape, and it makes about 2.5 turns. And it's going to connect to the vestibule at its base. And as I said before, it's going to be involved in hearing. The hair cells that are able to kind of respond to the pressure waves that are a result of sound waves are going to, or indirectly the result of sound waves, are going to stimulate nerves that are embedding the cochlea. The nerve that embeds the cochlea is the cochlear nerve, and it is actually one component of the vestibulocochlear nerve, which is going to be a cranial nerve of the brain. Let's look into the internal structure of the cochlea. These will be important when we talk about the physiology in more detail later. So here we're going to have part of the bony labyrinth. We can kind of see the border here. And the membranous labyrinth is actually going to create the cochlear duct. It's going to be located here. And the cochlear duct is going to travel through the length of the cochlea, now all the way to the end. And this cochlear duct is going to be filled with the endolymph because it is part of that membranous labyrinth. On either side, we're going to have two other kind of areas. We're going to have the sclera vestibuli. The sclera vestibuli will travel from the oval window to the end of the cochlea and eventually turn around to become this sclera tympani. The sclera tympani will go from the end of the cochlea all the way back to the round window where it can help alleviate pressure. So this is the scala vestibuli and this scala tympani. over here. And both of these are going to be part of the bony labyrinth, and they'll be filled with perilymph. So this is showing kind of a cross-section of the cochlea. We see the cochlear duct filled with the endolymph. There's going to be a special structure that we'll learn about in just a moment. We have this scala vestibuli and the scala tympani. If you're curious about what scala means, it actually means ladder. Okay. This image is actually showing kind of the cochlea laid out a little bit, and it's showing how the pressure waves are traveling through the perilymph of the fluid. What you see here is this over here is going to be this scala vestibuli. The oval window, my apologies, the oval window is going to be attached to the scala vestibuli, and the stapes is going to vibrate back and forth against the oval window, and these pressure waves will travel through the scala vestibuli. The scala vestibuli will loop around at a place called the helicotrema. Oh, I'm getting tongue-tied with that. And eventually become the scala tympani. The pressure waves can travel through the scala tympani and travel back to the round window, and the round window will move back and forth to alleviate the pressure waves. In the middle, we're going to have the membranous labyrinth, and here the membranous labyrinth is going to form the cochlear duct. We'll see sometimes the pressure waves will take a shortcut through the cochlear duct. So we'll learn about that more later on. Okay. So, So there's going to be specialized structures that are going to be important for the cochlear duct and allowing for us to hear the sound waves. There's a membrane that separates the scala vestibuli and the cochlear duct. We call this the vestibular membrane. This will be important because the sound waves could actually travel through the pressure waves can actually vibrate and travel through the scala vestibuli into the cochlear duct using this membrane. The organ that is very important and the membrane that is very important is the basilar membrane. Here, just trying to find my cursor. The basilar membrane is found at the base over here, and it's going to be closer to the scala tympani. And the basilar membrane is important because it will have a special structure called the spiral organ attached to it. So I do want to kind of look at the spiral organ a little bit bigger. So over here, what we're going to have is we're going to have the basilar membrane with a spiral organ attached to it. The spiral organ is going to be the structure that is going to be responsible for converting those pressure waves into an action potential because it contains hair cells inside. So the two types of cells that we have in the spiral organ is the supporting cells. These are going to just be epithelial cells that are going to help the structure of the spiral organ. But then there's going to be very special cells called hair cells. These are going to be the receptor cells. These cells will have stereocilia on the top. These are specialized kind of microvilli. And these stereocilia will be embedded into an area called the tectoral membrane. When the pressure waves actually travel through the cochlea, there will be times where the basilar membrane will vibrate back and forth with those pressure waves. And as the basilar membrane vibrates back and forth with those pressure waves, it will actually push the spiral organ into the tectoral membrane. The tectoral membrane is going to stay stationary, and because of this vibration and this stationary structure of the tectoral membrane, the hair cells will actually bend as a result. This bending will activate the hair cells, and when those hair cells become activated, they will release a neurotransmitter onto the sensory neuron, and that sensory neuron will eventually send that information into the cochlear nerve. So this spiral organ plays a really important role in allowing for that pressure wave to be converted into an action potential, an electrical impulse that the brain can understand. Those are the structures really important for hearing. Now what I'd like to do is look at the structures that are important for equilibrium and balance. So over here, we are going to have an area called a vestibule. Vestibule means entryway. And within that vestibule, we're going to have two areas. We're going to have the utricle and the saccule. The utricle and the saccule are actually composed of that membranous labyrinth. So this over here would be the utricle. It's continuous with the semicircular canals. And here we have the saccule, which is going to be continuous with the cochlea. I always remember U shape for utricle and snail for saccule to remember which is which. These structures are going to be important for static equilibrium. Really, they're going to tell us whether or not our head is tilted or not when we're looking at the static equilibrium. And it's also going to be important for linear acceleration. So an example of that is if you are riding a roller coaster and there's that first acceleration going forward and you feel like you're being pushed back into your seat, that would be a linear acceleration. And so it's going to be able to kind of feel and detect whether or not you are moving forward. There's an airplane going by, so I'm sorry. The mic is picking that up. Within the utricle and saccule, we're going to have a special structure called the macula. This is going to be the macula. It will be located here and here. And the macula is going to have the hair cells that are going to detect that tilting of the head or the linear acceleration. It's going to have two types of cells within it. It's going to have the supporting cells, so over here, and then it's going to have the hair cells located here. These hair cells are going to be capable of stimulating the vestibular nerve. The vestibular nerve and the cochlear nerve will combine together and eventually become the vestibulocochlear nerve, one of those specialized cranial nerves that will go to the brain. So let's look a little bit closer into the structure of the macula. Within the macula, we said that there are going to be hair cells. The hair cells are going to have the stereocilia, which are going to be a special type of microvilli, and a kinocilium, which is a true cilium that is extending upwards. These cilia are going to be embedded into a jelly-like membrane called the otolith membrane. So it's going to be embedded within this membrane. The otolith membrane is going to be kind of cool because it has all of these tiny little otoliths, these little ear stones embedded into it. And These ear stones are composed of calcium carbonate crystals. We'll talk about it more when we get into the physiology, but what happens with understanding linear acceleration is that these otoliths and these jelly-like membrane is going to have a high inertia because they are pretty heavy. So when we are stationary, they're going to like to stay in position. And when we move forward, what will happen is the hair cells and the supporting cells will be able to move faster than the otoliths and the otolith membrane. And so what will happen is it will actually bend the hair cells as a result, and leading to that perception of acceleration. I'll get more into it in a little bit. Fun fact, one a few years ago when I first started teaching, one of these otoliths in my ear got dislodged, and it went from my utricle and kind of stuck itself into my semicircular canal, and it kind of caused a lot of havoc there. The semicircular canals are meant for understanding rotational acceleration, whether or not you're spinning or not. And so what happened is that otolith kept on activating the hair cells within the semicircular canal, and it just made me feel like I was spinning constantly. And so it made me feel the drunkest I've ever felt in my entire life, and it was so bad. But fortunately, I got to go to the doctor, and they knew exactly what was happening. And I asked them, how am I going to be able to get this otolith out of my semicircular canal? And the way to do it is they actually had me sit on the table, and they slammed my back against the table in different directions to knock it out. It didn't work the first time, so I had to continue to do that until it finally came out. It took about 2 weeks. So imagine that being the drunkest feeling you've ever felt in your life, and then having to be like that for 2 weeks straight. Oh gosh, it was bad. But fortunately, it finally came out of the semicircular canal and things are fine. So yeah, weird stories. Speaking of semicircular canals, that's the next structure I'd like you to be familiar with. Connected to the vestibule, we're going to have 3 loops called the semicircular canals. There is going to be the anterior loop, posterior loop, and lateral loop, or anterior semicircular canal, posterior and lateral semicircular canal. And these canals are important because they're actually going to lie on the 3-dimensional planes of 3D space. And they're going to help us understand rotational acceleration. So if you're spinning in a circle or something like that, your semicircular canals will tell you how you're spinning. Are you spinning in place, staying on your feet, or are you rotating around, like head over heels, you know? So how are you spinning in space? I can do this because the semicircular canals are going to be lined with the membranous labyrinth, and the membranous labyrinth will actually be called the semicircular ducts within the semicircular canals. And this membranous labyrinth is actually filled with endolymph. And when we spin, this endolymph will actually move. And at the end of the semicircular canals, we're going to have a special region called the ampulla. The ampulla is a widened region of the bony and membranous labyrinth. So here we would have the semicircular canal and the widened part of the ampulla. Within the ampulla, there is a sensory structure called, called the crista ampullaris. The crista ampullaris is a specialized membrane composed of supporting cells and hair cells. And just like the macula, the hair cells are going to be embedded into a jelly-like substance, and we call this jelly-like substance the cupula right here. Let me get to a bigger picture. There we go. So over here you can see the crista ampullaris, and the crista ampullaris is going to have supporting cells, but it's also going to have hair cells, and those hair cells are going to have the kinocilium and the stereocilia. These are the hairs that will extend into the cupula. And when the cupula moves in response to the movement of the endolymph, these hair cells will become activated. And when activated, they're going to stimulate the vestibular nerve over here. So the hair cells in the semicircular canal and the hair cells within the vestibules, like the utricle and saccule, will both stimulate the vestibular nerve. The hair cells in the cochlea will stimulate the cochlear nerve. And together they will combine to form the vestibular cochlear nerve, which is going to be the cranial nerve that will be able to send information about hearing and equilibrium to the brain. In our next video, we're going to kind of take these pieces and put them together. We're going to go through step by step the physiology of hearing, and then we're going to look at the physiology of equilibrium in our third video. Thank you for listening and have a wonderful day, and be good to yourselves. Bye-bye.